Question 8 starts with state what's meant by the wave-particle duality of electromagnetic radiation. Now your answer will be acceptable if you say that sometimes radiation behaves as a wave and sometimes it behaves as a particle. Personally, I prefer to say that wave-particle duality means that sometimes the behaviour of radiation is best explained in terms of waves, and on other occasions the behaviour of radiation is best explained in terms of particles. I'm not going to bother writing that in, you can though. Next part, which aspect of the dual nature of electromagnetic radiation is demonstrated by the photoelectric effect? Again, I'm not going to bother writing this in, you have to write it in. And it is very important that you do actually practice doing written answers for questions. A lot of people think that when doing practice questions, just do calculations and you rely on being able to blag the written answers in an exam. It doesn't work like that. You do need to practice expressing your ideas in words. So I'm not going to tell you the answer to this, but I am going to remind you that we used to think that radiation was just waves until we came across the photoelectric effect. So I think I'm more or less giving you the answer to that one. Part B. Now for this, it's just like the question in the book, except I've changed the numbers, so I'll get different answers. So a metal plate is illuminated with ultraviolet radiation of frequency 2.07 times 10 to the 15 Hz. The maximum kinetic energy of the liberated electrons is 2.9 times 10 to the minus 19 joules, and it asks for the work function of the metal. So we know we're dealing with a photoelectric effect, so we need to think of the equation. If we can't think of the equation, we'll look it up on the datasheet. And there's the equation that you'd have available in the exam. HF equals phi plus EK max. So HF equals phi plus EK max, which of course is TK max's brother. What are all these terms? Well, hopefully we'll realise that HF is the energy of the photon that's causing the effect, that brings the energy in. Phi is the work function of the metal. That's how much energy is needed to get the easiest electrons to leave the surface, And EK max, that's how much kinetic energy the electrons will have if they're the ones that are easiest to get off the surface. Electrons that are more difficult to get off the surface require more energy than that, and therefore they've got less kinetic energy left over. So that's why the max is there. So calculate the work function. Well, it tells us the frequency, it tells us EK max, so we can find the work function. I'm going to rearrange the equation before I put the numbers in. So the work function, well, we can either follow rules of algebra or just use common sense. If these two things added together give that one, then this thing must be the difference between them. So it tells the frequency, so 6.63 times 10 to the minus 34 is Planck's constant, times the frequency, 2.07 times 10 to the 15, minus EK max, 2.9 times 10 to the minus 19, and that gives us a work function of 1.08 times 10 to the minus 18 joules. You'll get a different answer, but you should use the same method. The radiation is maintained at the same frequency, but the intensity is halved. State what changes, if any, occur to the number of electrons released per second and to the maximum kinetic energy of these electrons. So we're going to think about what this word intensity means. I know the question is about ultraviolet radiation, but let's think what intensity means. If it was visible radiation, the intensity would be the brightness. It would be how much energy there is every second. So for ultraviolet, we can't really use the word brightness, but it still means the same thing, it's the amount of energy per second. When I to this question, by the way, it talks about halving the intensity. The original one in the book is to do with doubling the intensity. So if the intensity is halved, that means you're only getting half as much energy every second. But this energy is coming in lots of little photons. Each photon brings energy, and all the photons have got the same energy. So if you're going to have half as much energy every second, but the photons are still the same, you should be able to work out what must happen to the number of photons every second. It's not difficult. And then if you think what's happened to the number of photons that are hitting the surface every second, every time an electron releases, it's because you've had a photon hit. If you've changed the number of photons hitting every second, think how that would change the number of electrons that are emitted every second. Again, it's not difficult. The next bit, the maximum kinetic energy. Now it says that the radiation's got the same frequency, it's just not as bright. If it's got the same frequency, then that must mean that the photons have the same energy. So you've got a different number of photons hitting the surface every second, but the photons have still got as much energy. When we go back to our equation, if the photons have got the same energy, and it's the same material, what can we conclude about the maximum kinetic energy of the electrons that are emitted? The last part, the metal plate is replaced by another metal plate made of a different material. And we know that each material has a particular value of work function, so a different material will have a different work function. Now it says that you illuminate the new material with the same radiation as before, but no electrons are liberated. In other words, the photoelectric effect doesn't happen. So in other words, the photons don't have enough energy to liberate electrons anymore. So from that you should conclude what that tells us about the work function of the new material. It's not the same as the value before. What can you say about it? How is it different?